Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are going to start the 16th lecture of Discrete Structures CSC 102. In the previous lecture we have started the relations. We have discussed some basic concepts of relation. We have discussed also one-to-one, many-to-many, one-to-many and many-to-one relations. We have also discussed a relation on a set and inverse of a relation, and I have told you that we shall discuss in the next lecture representing relations using digraphs and array relations, because in the previous lecture we had not enough time. So along with these two topics we shall discuss also some properties of relations, which are reflexive, symmetric and transitive properties. We shall also discuss the less than relations, and we shall discuss these properties of reflexive, symmetric and transitive with respect to less than relation. We shall also discuss congruous, modulo 3 relations, and then we shall see what is the transitive closure of a relation. How we represent relations using digraphs or directed graphs. So by definition, a directed graph or digraph consists of a set V of vertices. Vertices can also be, we can also say them nodes, together with a set E of ordered pairs, together with a set E of ordered pairs of elements of V, which are called edges or arcs. The vertex A is called the initial vertex and the edge AB, and this is called basically the initial vertex. This is called the terminal vertex, and AB ordered pair is called the basically edges. These are edges, ordered pair. We use usually the arrows to display the graphs. We try now to understand all these concepts with the help of examples. First, we take this example. For example, if we have V set, this is a V set which contains vertices A, B, C, D, as we can say that, consist of vertices or nodes. The elements of V are called vertices or nodes, and together with set E of ordered pairs of the elements of V. E is basically the relation. E, we have defined this relation. A is related to B, A is related to D, B is related to B, B is related to D, C is related to A, C is related to B, and D is related to B. Under some relation E, we are not defining here what is the relation, but we know only that these elements are related under some relation E, because we here try to understand how to construct the directed graphs of which represents the relations. So now here there are edges. AB ordered pair is edge. This is also edge, 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 and these are all edges, because the set E of ordered pairs of elements of V called edges, or we say them arcs. And we have initial vertex and terminal or final vertex, and we display the relation. We show the relation between two elements A and B by drawing arrows between these two vertices. Now how to construct this digraph? First of all, we write elements A, B, C and D in circles. You can write circles also. Now we see what is the relation E. Now this is the relation E. A is related to B, the first ordered pair. So A is related to B. We draw an arrow from A to B whose direction is from A to B. Now A is related to D. A is related to D means we draw a line or an arrow from A to D, just like this here we have drawn. B is related to B. Now how we express this relation between two same elements, B is related to B. We draw an arrow which starts from here and which ends here also. So we draw this type of arrow or a loop. We call it this edge as a loop. So if an element is related to itself, we in a directed graph we express it as we draw an arrow which starts from here and which ends also here. An edge of the form B is called a loop. Now next is B is related to D, so we draw an arrow from B to D. C is related to A. Now we draw an arrow from C to A as we have drawn here, and similarly D is related to B and we draw an arrow from here to here. So this is how we can construct a digraph or a directed graph which represents the relation on a set. So I hope you understand how we construct the digraphs which represents the relation on a set. Now we consider another example, a real example, in which we define the relation also. Let A be a set 3, 4, 5, 6, 7, 8 and define a relation R on A as follows. How we define? The two elements of A, X and Y, are related. X is related to Y if and only if 2 divides X minus Y. This is basically the modulo 2 relation, congruous modulo 2 relation. I hope you know it already, we have discussed it. Draw the directed graph of R. Now we have to draw the graph. First of all, we have to calculate the elements of the relation. That is, we shall find which elements of A are related under this relation to which elements. Note that every element is related to itself. First, 3 is related to 3 because 3 minus 3 is 0 and 2 divides 0. Similarly, 4 minus 4 is 0, therefore 4 is related to 4. 5 minus 5 minus 5 is 0, therefore 5 is related to 5. Similarly, 6 is related to 6, 7 is related to 7, 8 is related to 8 because 2 divides 6 minus 6, which is 0. 2 divides 7 minus 7, 2 divides 8 minus 8. So every element is related to itself. That is what we know until now. Thus there is a loop from 3 to itself, 4 to itself, from 5 to itself, and so forth, because every element in A is related to itself. So we have in a relation, we have, if R is the relation, then the elements in the relation we have, first of all, 3 3, 4 4, 5 5, 6 6, 7 7, 8 8, and there are other elements which we shall find. We have to find. So first of all, we know that every element is related to itself. Now we have to find the other elements which belongs to this relation. Note that now the elements in which the difference is 2, they are also related, because 3 is not related to 4, because the difference between 3 and 4 is not the multiple of 2, because the difference between 3 and 4 is 1. So 2 doesn't divide 1, so 3 and 4 are not related. 3 and 5, the difference between 3 and 5 is 2, which is a multiple of 2, therefore 2 divides 3 minus 5 and 5 minus 3. So 3 is related to 5 and 5 is related to 3. Similarly, now we check 3 and 6. 3 minus 6 and 6 minus 3 is basically 3 or minus 3, which is not the multiple of 2, therefore 2 doesn't divide 3 minus 6 and 3 and 6 are not related. Similarly, 6 and 3 are not related. Now 3 and 7, we check them. 3 minus 7 or 7 minus 3 is 4 or minus 4. Therefore, and 4 is the multiple of 2. Therefore, 3 and 7 are related. Similarly, 7 and 3 are related. Now we check 3 and 8. 3 and 8, 3 minus 8 is 5 or 8 minus 3. 3 minus 8 is minus 5 and 8 minus 3 is 5, and we can and 5 is not multiple of 2. Therefore 3 and 8 or 8 and 3 are not related. So now we are in the position to write all ordered pairs which comes in the relation. So here we can write the other elements of the relation, which are 3 5 5 3 and 3 7 7 3 and 5 7 and 7 5 and 6 8 and 8 6. So we have 3 4 6, and also we have 4 6 4 6 and 6 4. Similarly, we can write all the ordered pairs which comes in the relation. So now we are in the position to draw the directed graph. Now we write the elements of A in a circle, in a square, in whatever, in some pattern, just to mark the arrows between the two elements. Here in the previous example we had 4 elements, therefore we write them in this way. If we have more elements, then just write them in some order, just to draw the appropriate graph. Now in the previous slide we have seen that every element is related to itself, means 3 is related to 3, 4 is related to 4, 5 is related to 5, 6 is related to 6, 7 is, and so on. Now it means if we write 3 4 5 6 7 8, 3, how we express that 3 is related to 3? We start an edge, we start from 3 and ends on 3 also, which is a loop we have discussed in the previous slide. So at every point, at every element, there is a loop. There is a loop which starts from here and which ends here. At every element from 4 5 6 7 8, because every element is related to itself. Now 3 is related to 5, we draw an arrow from 3 to 5, and 5 is related to 3, an arrow from 5 to 3, and 4 is related to 8, we draw an arrow from 4 to 8, and 8 is related to 4. Similarly, we have drawn arrows from the elements to the elements which are related under this relation, and we have constructed the directed graph. So this is how we can express the relations using directed graphs or digraphs. And similarly, by watching digraphs, we can write the relations, which is the reverse of this process. As you can see here, that if we are given this graph, we can easily write the given relation, because we know that A is related to B, B is related to itself B, C is related to B, C is related to A, B is related to D, D is related to B, and by watching arrows and elements, vertices and edges of the digraph, we can write the relation from the digraph. So here in these two examples we have learned how to draw a digraph from a given relation. Similarly, if we are given a digraph or a directed graph, we can write the relation, what relation this digraph shows. So these these two examples are basically the examples of directed graphs which shows the relation. Now we see what is an N-ary relation. N-ary relation, we generalize the concept of binary relation to N-ary relation. This is basically binary or N-ary relation. In N-ary relation, a binary relation is a subset of Cartesian product of two sets. Similarly, an N-ary relation is a subset of Cartesian product of n sets. This is the obvious thing, as we have studied in Cartesian product. Any relation is basically the subset of Cartesian products of two sets or one set A cross A. Now the N-ary relation is basically, we generalize the concept of binary relation to n sets. If we are given n sets, A1 and A2 and so on, an N-ary relation R, the relation is represented by same letter R, an N-ary relation R on, now here we have the Cartesian product of n sets, means that if we have A1, A2, An, then the Cartesian product of n sets is A2 cross An. Now the R relation which is defined on these sets is basically the subset of the Cartesian product of these n sets. Its special case, if n is 2, we get the binary relation. If n is 3, we get the 3-ary relation or ternary relation, we can say it. If n is 4, for example, we have 4 sets, then we can define A1 cross A2 cross A3 cross A4. Now the relation is basically the subset of this. The relation which is basically the subset of these, the Cartesian product of these 4 sets is called basically quaternary relation. So the special cases of this N-ary relation are basically binary, ternary and quaternary relations respectively. The sets A1, A2, An are called domains basically, and n is called the degree of this relation. Now we take an example of the ternary relation. If we are given a relation R which contains triplets, we can say it, we can say the ordered pair, basically a pair of 2 elements is ordered pair, and a pair of 3 elements ABC is basically called a triplet. So this is ordered pair, and this is triplet pair, or you can say it, or contains triplets such that A is 2B, and here this relation is the basically the conjunction between two relations, and B is equal to 2C with A, B, C belongs to N. I hope you know what is N here. N is basically the set of natural numbers. Now what is the degree of this relation? The degree is obviously 3 because N is 3 here, and its elements are triples or triplets, as I told you. What are its domains? Its domains are the set of natural numbers. In basically here R is the subset of n cross n cross n, because we have this relation which defined on n cross n cross n, because the domain in each case is n and n. Now is 2, 4, 8 belongs to this R or not? 2 is not the multiple of basically some B, some integer. 2 is not multiple of this. So therefore, and B, basically B is not also the multiple of some integer C, where these two relations must be satisfied by the conjunction operator, because B must be the multiple of some integer and A must be the multiple of B. So this triplet doesn't belongs to R. But here we can say that A is basically 4, this is basically 2 into 2, and here this B is 2 is equal to 2 into 1. Now this we can take C as 1, B as 2, and 4 as A. So this triplet belongs to this relation. So such type of relation is basically ternary relation, and this is obviously the subset of n cross n cross n. A simple application of N-ary relation is in basically database. How to manage the data in computer. So consider a database of students, which basically usually we encounter in universities. If we have students, they have names, they have student ID number, they have major subject, and GPA. So we can define a relation which has the first element as the name of the student, the second is student ID, the third is student major, whether he is a computer science student, he is an engineering student, he is psychology student, or whatever. We can define his major, and at the end we can define his GPA. So this is how we can manage the data with the help of N-ary relations. So this is basically 4-ary relation, because we have 1, 2, 3, 4 elements in this, and we say them 4 tuples. The one element of this relation is basically called a 4 tuple. The elements are called 4 tuples. So this is basically a little basic application of N-ary relations in computer science. Now we start the properties of relations. How to classify the relations. The first definition in this regard is a relation R on a set A. A relation R on a set A is called reflexive. Reflexive if every element in A is related to itself. If every element in A is related to itself, means all elements of A are related to itself for every element of A. If there exists some element in A which is not related to itself, means if the ordered pair of that set AA is not in that relation, then we say that this relation is not reflexive. So here we have the stress on this statement for every element of A belongs to capital A. Now we check whether these relations are reflexive or not, which are defined on this set. Here the first relation is 1 1 1 2 1 2 3 3 3 4 4. We have this set. Whether every element of this set is related to itself in this relation or not, that is not true, because 1 is related to 1, 3 is related to 3, 4 is related to 4, here you can see, but 2 is not related to itself here in this relation, so this relation is not reflexive. In the second case, 1 is related to 1, 2 is related to 2, 3 is related to 3, 4 is related to 4. So all the elements of A are related to itself in this relation, so therefore this relation is reflexive. To check whether the relation is reflexive, we shall only check whether every element of the given set is related to itself or not. This is true for first, second, third, 4 element. There is an extra element here, we don't care about it. If there are extra elements, we don't care about them, we just need to check only whether every element of A is related to itself means these ordered pairs are present in R. If they are present, we don't care about the other ordered pairs which are present in that R. Then in this case that relation will be reflexive. Now we check the third. We have 1 1, 2 2, 3 3, but we don't have 4 4. 4 4 is not present in this relation, therefore this relation is not reflexive. So a relation on a set is not reflexive if there exists some element A belongs to A such that A doesn't belongs to R. So for a relation to be a reflexive relation, every element must be related to itself. So this is what the reflexive relation. Next we discuss some other type of relations where the symmetric, antisymmetric and asymmetric relations. By definition, a relation on a set A is called symmetric if I am repeating it 3 times because if BA belongs to R, whenever AB belongs to R, means for all AB belongs to R, BA, if AB belongs to R, then BA must also be in R for a relation to be symmetric. Means if here this relation 1 1 2 2 1 1 is in R and 1 1 is in R, means if we take the same element, it doesn't matter if we have different element AB. If we have 2 3 here but 3 2 is not present in this relation, 3 2 is not present in this relation, so this relation is not symmetric. So this is what we are saying here. If AB belongs to R, then BA must also be in R. So this is what when a relation will be called a symmetric relation. A relation on R, a relation R on a set A is called antisymmetric if AB belongs to R and BA belongs to R, only if A and B is equal to, sorry, A is equal to B. Means as in the previous case, 1 1 is present here, 2 2 is here, 3 3 is here, 4 4 is here. So this relation is antisymmetric also, because if A, B and BA belongs to R, then A is equal to B. So this is how we check whether a relation is antisymmetric or not. Now the third kind, a relation R on a set is called asymmetric. This is asymmetric, this is symmetric. This is basically the reverse of this. A relation R on a set A is called asymmetric if AB belongs to R implies that BA doesn't belongs to R for all AB belongs to A. This is so such if AB belongs to R, BA doesn't belongs to R, then we say that this relation is asymmetric. So for example, we take some examples of the relations and we check whether the given relation is symmetric, antisymmetric or asymmetric. Are the following relations this are symmetric, antisymmetric or asymmetric? The first is basically 1 belongs to 1, 1 belongs to 1, 2 belongs 1 belongs to 1 2 belongs to R, then 2 1 belongs to R also. So if AB belongs to R implies BA belongs to R. So this is true for all AB belongs to R. So this relation is symmetric. This relation is antisymmetric because if AB belongs to R and BA belongs to R implies A is equal to B. So this is true. So we can say that this relation is antisymmetric. Now this 1 3 3 2 2 1 1 3 belongs to, so if AB belongs to R implies BA doesn't belongs to R. 1 3 belongs to R, 3 1 doesn't belongs to R, 3 2 belongs to R, 2 3 doesn't belongs to R, 2 1 belongs to R, but 1 2 doesn't belongs to R. So this relation is an asymmetric. This relation is 4 4 3 3 1 4. This relation is antisymmetric because it satisfies. This relation is also antisymmetric. This relation is not antisymmetric. 4 4 3 3 1 4. Antisymmetric is basically if both here 1 4 and 4 1, because here 4 this doesn't belongs to this, implies 1 is equal to 4. We have to check this in the antisymmetric, but here 1 4 and 4 1, this is not true, so we cannot check this. So this relation is antisymmetric because the elements, these two elements which satisfy these two conditions, for these two conditions we are also, the conclusion is, or this condition is true, therefore this relation is also antisymmetric. And now we are going to discuss what is a transitive relation. A relation R on a set A is called transitive if or whenever AB belongs to R and BC belongs to R, then AC belongs to R. For ABC belongs to A. So here I stress on this fact that if AB and BC belongs to R implies AC belongs to R. Now if both these are true, then this must be true. If both of these are not true, we cannot check this. So for a relation to be transitive, these two conditions, this hypothesis completely must be true, then we have to check this condition, the conclusion must be true, as in the conditional statements. Are the following relations on this set 1 2 3 4 are transitive or not? Here this 1 1 1 2, now 1 is 1 related to 1 and 1 is related to 2. Now 1 must be related to 2, so 1 2 is present here. 2 is related to 2 and 2 is related to 1. Now 2 1 must be present here, so 2 1 is also here. Similarly, we can check all these possibilities for all elements, and we can check that this relation is transitive, because now we check the second relation. 1 is present here, 1 is related to 3 and 3 is related to 2, so we must have 1 is related to 2 must be in that relation also. Is 1 2 is present in this? No, this is not present in this relation, therefore this relation is not transitive. Similarly here 2 is related to 4, 4 is related to 2, so 2 must be related to 3 here. This is true. Now 4 is related to 3 and 2 is related to 4 and 4 is related to 3. 2 is related to 3. Now we can 2 is related to 3, yes, 2 is related to 3 and 2 is related to 4. So 2 must be related to 4, which is present also here, and some other possibility in which doesn't satisfy this condition we can search here. So there is no condition, there are no two ordered pair which violate these two conditions, therefore this relation must also be transitive, because 2 is related to 4, 4 is related to 3, 2 is related to 3, 4 is related to 3, but there is no relation of 3 to some other, and 2 is related to 4 is related to 1, and 1 is related to no. So this this relation must be transitive also. If we are unable transitive, so this is yes, this is not no. So this relation is also a transitive relation. So properties of we see another example in this by taking set A as 0, 1, 2, 3 and define the relation R as NT on the set A as follows. Check whether R is reflexive, symmetric, transitive. Is S is reflexive, symmetric, transitive, and we have to check T is reflexive, symmetric, transitive. Now first we choose the R, the relation R. We can use the directed graphs to check whether the given relation is reflexive, symmetric, or transitive or not. So first of all, we take the relation R and we draw the directed graph of R. How we draw the directed graph of R? You know, I repeat here, 0 is related to 0, so we write there are only 4 elements. We draw 4 circle, 1, 2, 3, 4. Here we write 0, 1, 2, 3. Now 0 is related to 0, so we draw a loop from 0 to 0. 0 is related to 1 and 1 is related to 0, so we draw the arrows as we do to construct the directed graphs. So after constructing this directed graph, how to check whether the relation given is reflexive, symmetric, or transitive? First we check whether the given relation is reflexive or not. If there is a loop at each element of A, we have a loop at 0, we have a loop at 1, we have a loop at 2, we have a loop at 3. So therefore this relation is reflexive, because a loop shows that this element is related to itself. So at every element there is a loop, therefore every element is related to itself. It means this relation R is reflexive. Now to check the symmetric property of the relation, here we have to check whether R is reflexive, symmetric, or transitive. Now how to check this relation is symmetric by using directed graphs. We can see here that if 0 is related to 1, 1 is related to 0, 0 is related to 3, 3 is related to 0. Now here 3 is not related to 2, so we don't need to check whether 2 is related to 3 or not. Similarly, 1 is not related to 2 and 2 is not related to 1. We don't care about it. We have to check only those pairs. For example, if 0 is related to 1, then 1 must be related to 0. If 0 is related to 3, 3 is related to 3. Similarly, 0 is related to 0, then 0 is related to 0. This is obvious to check A, B and BA, because both is 1, 1, 1 and 1, 1. So this is present here. So if AB belongs to R, then BA belongs to R. So this relation is also symmetric. Now we check whether this relation is transitive or not with the help of directed graphs. Now you can see that if 3 is related to 0 and 0 is related to 1, but 3 is not related to 1 because there is no directed arrow from 0 to 1. There is no directed arrow from 3 to 1. Therefore this violates the transitive property of the relations. Therefore this relation is not transitive. So this relation is reflexive. This relation is you can say this relation is reflexive, symmetric, but not transitive. This is how we can check these three properties: reflexive property, symmetric and transitive property, using directed graphs. Now we consider the second relation, and we shall check whether this relation is symmetric, transitive or reflexive. Now this relation can be 0 0, 0 2, 0 3, 2 3. We draw the elements 0 1 2 3 and we draw the arrows to represent this relation. In short, we constructed a directed graph. Now if we look at the directed graph, we can obviously we say that every element is not related to itself, because there is not a loop at every element. Therefore this relation is not reflexive. If 0 is related to 2, then 2 is not related to 0. Therefore this is not symmetric. Transitive. Now we check whether this relation is transitive or not. When 0 is related to 2 and 2 is related to 3, 0 is related to 3. When 0 is related to 0 and 0 related to 2, then 0 is related to 2. So every possibility of the transitive property this directed graph satisfies. So this relation is transitive. So this relation is basically not reflexive, not symmetric, but this relation is transitive. So with the help of directed graphs, we can easily see, we can easily investigate that whether the given relation is reflexive, symmetric or transitive. The last relation T is not reflexive, obviously. It's not symmetric, obviously, but it is transitive. How? Because we cannot check or I left this exercise, this relation for you as an exercise. This relation is not reflexive and not symmetric, but it is transitive. Here this relation is transitive. I left this as an exercise for you. You have to answer whether the given relation is reflexive, symmetric or transitive or not. Now the next is properties of the relation. How many different reflexive relations can be defined on a set A containing n elements? In the earlier slides we have calculated that how many relations we can define on a set. Now we are going to define how many different reflexive relations can be defined on a set containing n elements. Relations on R are basically, subsets of A cross A, which contains n square elements. We have discussed it already. Therefore different relations on A can be generated by choosing different subsets out of these n square elements. So there are 2 power n square relations. Now as we know that a reflexive relation must contain n elements, AA, for every element in A. So a reflexive relation must contain these n elements, and other it may contain or it may not contain. So how we can say that how many different reflexive relations we can define? So consequently we can choose only n square minus n elements, because n we have subtracted from the total elements. Why we have subtracted? Because these n elements must be present in the relation. So therefore we have subtracted these n elements, because we cannot delete or we cannot eliminate these elements from any relation. All the relations which can we define, all the reflexive relations which we can define on a set, all relation must contain these elements. So therefore we subtracted these elements from the all possible elements. So if n square minus n is equal to n into n minus 1, and the rest of elements we have n into n minus 1, so on the same manner as we have calculated 2 power n square, we can say that the relation, reflexive relations which we can define on any set is basically 2 power n into n minus 1. This is very simple. I hope you understand. So now we are going to discuss the properties of less than relation. We shall prove that whether this less than relation is reflexive, symmetric or transitive or not. So this is what we are demanded here in the question. We define a relation on R. Relation here R is this relation and this R is set of real numbers as follows. For all x y belongs to R, x is related to this R is basically the bold. This is the set of real numbers. X is related to y through R if x is less than y. So we have to check whether this relation is reflexive, symmetric or transitive or not. So first we check whether R is reflexive. R is not reflexive because under this relation every element is not less than that element. For example, if we have 1 is not less than 1. This is not true. Basically this is true, 1 is not less than 1, but 1 is less than 1. This is not true. So every element cannot be connected to itself through this relation. Therefore this relation of less than is not reflexive. Similarly, we can show that R is not symmetric because this relation of less than is not symmetric, because if x is less than y, then y is not less than x. This is not true. If x is less than y, then y is not less than x. This is not basically true. As an example, if we take 1 is less than 2, and this doesn't imply that 2 is less than 1. Therefore this relation is not symmetric. By the definition of R, this means that this if x is less than R, then y is less than x, but this is false. There exists x y belongs to R. So this here we can give a counter example to disprove this statement that this relation is symmetric. As we have studied what is the counter example in when we have studied methods of proofs. Now this relation is reflexive. The only property with the less than transitive. This relation is transitive. The only property which this relation satisfies the transitivity. R is not transitive. R is basically here transitive. R is transitive. Here it is a mistake that R is not transitive, but R is transitive. If we want to show that R is transitive, what is the condition to be verified that a relation is transitive? For all x, y, z belongs to R, if x is related to y and y is related to z, then we check whether x is related to z or not. So by definition, if x is less than y and y is less than z, then x is obviously less than z. If x is less than y and y is less than z, it implies x is less than z. So this is satisfied, this property. So therefore this less than relation is transitive. but less than relation is not reflexive, not symmetric, but it is transitive. Now we take another example of the congruence modulo 3, and we are going to prove whether this relation is reflexive, symmetric and transitive or not. Define a relation T on Z. Z is the set of integers, and for all integers M is related to N under the relation T if 3 divides N minus N. This is called basically the congruence modulo 3 relation. So you can see here that T is reflexive because M minus 1, M minus M, because same element. We have to show that M is related to M to be T is reflexive. If M minus M is 0, then 3 divides 0. Every number divides 0. So 3 is basically 0 is equal to 3 into 0. We can write it as. Hence 3 divides M minus M. Thus by definition of T, M is related to M under the relation T. Therefore T is reflexive. T is symmetric also. This relation T is symmetric. Suppose M and N are particularly but arbitrarily chosen integers that satisfy the condition that M is related to N under the relation T. So to prove symmetric, what we prove, if M is related to N, we have to prove N must be related to M. This is what we have to prove. So if 3 divides M minus N, then by definition, or divides, this means M minus N is equal to 3k. There exists some integer k. If we multiply by minus 1 on both sides, we get what? N minus M is equal to 3 into minus k. What does it mean? K, if k is integer, minus k is also integer. This implies that 3 divides N minus M. So this equation shows that 3 divides N minus M, and therefore this is N is related to M under the relation T. So we have shown that if M is related to N under the relation T, then N is also related to M. So this relation T is symmetric. So now similarly we can prove that the congruence modulo 3 relation is transitive. You can see here, and this I left as an exercise for you, that T is transitive. So congruence modulo 3 relation is reflexive, symmetric and transitive also. So for today it's enough, I think, and we stop here, and we summarize the topics which we have studied today. We have discussed we have discussed N-ary relations. We have discussed also how to represent the relations using digraphs. We have discussed some properties of relations which are reflexive, symmetric and transitive properties. We have discussed the less than relation and congruence modulo 3 relation. We shall discuss the transitive closure of the relation in the next lecture, because today we don't have enough time. So till the next lecture, Allah Hafiz.